No. I read like yesterday because it was like on the like required reading list. And then I was gonna read it yesterday and I haven't read it in my project yet. To be yet. So I decided not to read that for other stuff.
Next.
I set the heartbeats, but I don't.
So yeah, with that.
Yeah. That one's like okay. I haven't had any time to work on it, and he's been like really, it's actually probably not. I live kind of far away, so I think an hour and a half. So the front runner has Wi-Fi. It's not like the comfortablest setup.
Yeah, it's usually yeah.
I made a change because I used to ride Red Line and like you pretty much no, it's just really crowded. There's no Wi-Fi, so it doesn't work where it don't require Wi-Fi. You're like sitting like this, trying to hold all your stuff. So I live in Syracuse. That's where so I work in
You work there?
well, it ends in May, so it's a student engineer. They have like some role that talked to him about it, but I like told my wife I'd be in school 2 years. That's good. Yeah. I was like, well, just take one class, extend it just a year. And I will. She's like, I don't know, so that's good. So, yeah, she's a teacher, 6th grade teacher. 6 years. So she's got a nice job because it's 5 minutes away. Definitely a good year this month. Takes some experience. Well, I figured there was some unsaid rule that you don't hold class after a test. I was just joking.
That's a good distribution system too.
Yeah. Which you can see it, he's always like, down the bar, that's one cool ceremony. I mean, I think it's important to understand just because it wouldn't do anyone good if you just talk or just sat there. Yeah, they're really nice. That's what I gotta figure that out. This semester.
Alright, it's about part. So, how's everything? Project, interns, also good. Yeah. So, we will probably finish the grading by the end of next week. So it's a little bit too long right now, but we've been really busy this week and next week. So sorry, but we will be able to finish that by the end of next week. And also, next week we will cancel all the office hour. So, so if you have any questions or concerns, you can still send us an email or send a message in Canvas. Okay. On the week after next week, everything goes to normal, like office hours. Okay. And so I don't think we will release the next lab next week. Maybe the week after. So don't worry about that. Okay. So about the midterm. So how's it? How did you do over the midterm? Do you think it's good or bad? I would say as long as you write something, don't worry too much. Okay, it will be really easy one for you. Okay, so don't worry too much. Okay. And since it's only like 25% of the final grade, so you still have a lot of chance even if you don't do good. Okay.
Did you say there was a curve in this class?
We didn't do it last year. I don't know if we need to do it this year. So
What if it's, if you see that it is, there would be.
right. So if the grade, like if the average is too low and we find there are basically everybody is failing, maybe we'll do a curve. Okay, but for my, I just did a quick scan over the papers. I don't think that's the case, so that's probably won't happen. Okay. Yeah. So after the grading, once we release the grades, you can come to office hour to like get your own paper and try to if you have some concerns about the grading, you can let us know. Okay. So let's continue with the lecture. So this is the second half of this lecture. Although this lecture will be still on the same topic, access method, and different access path. Okay, so external sorting is a slightly I would say unrelated topic than the previous topics you've already seen, because it's more like implementation of a particular operator. But we'll just put it here because this is some implementation details, and it usually counts as one of the access path of your code. So that's why it's fit here. After this, we will talk about query evaluation, query optimization, transaction, concurrency control, and you're done. Then by then you'll be done with all the course material. And after that, I would expect there will be probably 2 to 3 lectures left. Then I will cover some other topics that you might be interested in. Okay? We will do a survey on what topics you might want me to cover in those additional lecture lectures. Yeah.
If you don't cover all the topics, will you make the slides available for the things that you don't cover?
So I have a bunch of slides made by Pepe before, so I can post those on Canvas. And if you decide you do not want those topics, you want something else, and I think I can cover those. Like if I have the knowledge to cover those, I will make some new slides as well. Okay. So okay, that's about it. So let's continue with external sorting. So sorting is quite basic algorithm in computer science, right? You can, if I give you an array of integers, you can basically use whatever sorting algorithms. They're basically all in the standard library. You have quick sort, you have merge sort, heap sort, or some simpler sorting algorithm like bubble sort, inserting sort, right? And there's a joke. Sorry, there's a algorithm called logo sort, which is basically you are given a monkey, and you let the monkey to randomly swap, like shuffle the array and see if it's more. Not then let the monkey shuffle it again, and you will have some chance to get a sorted array this way. That's just a joke. It's called logo sort. Anyway, so what's different from that with this external sorting? So basically, if you are given an array that's in memory, right? It's already in memory, and memory has the property that the random access is fast. You can basically access whatever element at whatever index in O1 time, okay? Or with a small overhead. So that means basically in almost all the algorithms you see before, they make use of random access. Like if you do quick sorting, if you do a quick sort, the key operation is called partition. Basically, you pick one of the key as a pivot, then partition the array into 2 parts. One is smaller than that particular elements, and the other part is larger than that. And once you do this recursively, you get a sorted array, and that's quick sort, right? So, but that actually doesn't work on an external setting, right? If you have a disk, remember the random access on disk are really slow. It's almost like 20 times slower than sequential I/O. So if you do this, if you have a huge array on the disk, then you do a quick sort. It's not quick. It's really slow. Okay, so that's not reasonable. To handle that, so basically we are trying to sort a huge amount of data in a very small memory. Okay, suppose you have a 1 gigabyte of data, but you only have 1 megabyte of memory. Then that's our problem, right? And actually, so why don't we just use the virtual memory? Because virtual memory is basically I give you a virtual memory space. You can do an mmap, then it's in a virtual memory space, the file, right? The file is in a virtual memory space. Then you can apply whatever in-memory sorting algorithm to that. But the issue there is really you only have 1 megabyte of memory. So the OS will do all the heavy lifting for you. It will swap in the page when you run out of space, and you access some page that's not in memory. So that basically means if you have a very small memory and a huge file, you basically pay 1 IO per access. That's huge. That's still like the same as if you just do sorting, in-memory sorting, directly adapt the in-memory sorting algorithm to an external memory. So that's not going to work. So here, what we are trying to do is we're trying to reduce the number of IOs as much as possible. We are not really concerned about CPU cost, although it's a factor, but it's not really important. The real thing matters is we want to pay as little IO as possible. Also, we might want to do sequential IO if it is possible. Okay. So, a naive way to do that, we can actually adapt the merge sort, the in-memory merge sort to an external memory merge sort. The way to do that, so remember, merge sort is basically you recursively partition the whole array into smaller ranges. So basically, if you have a whole bunch of elements, say it's 5, 6, 8, 7, 4, 3, 1, 2, correct? Then if I'm doing a merge sort in memory, it's basically these are the numbers I'm trying to sort. So basically, you divide the array into half, and you recursively do this merge sort until. So basically, you recursively divide those arrays until you reach a single element. So basically, if you divide the array into a bunch of single element arrays, they are already sorted, these single element arrays, right? And when you are coming back, so suppose you come back from 5 and 6, you have 2 sorted arrays, which is 5 and 6. And you merge them into a sorted one. That's going to cost you a linear scan, right? So basically, this is 5 and 6. And when you come back from 8 and 7, that's 2 arrays. So you rearrange those 2 arrays using a linear scan and get 7 and 8 instead of 7 and 8 instead of 8 and 7. And do the same on this and on this. Okay. Then you get a lot of length 2 sorted arrays, and then you merge 2 of them, every 2 of them. So basically, if you have 5, 6, 7, 8, you merge them into 5, 6, 7, 8, and then for the second half, you merge 3, 4, 1, 2 into a sorted array of length 4. So that's going to be 1, 2, 3, 4, right? And finally, you have 2 sorted arrays, and you want to merge them into 1 sorted array. So basically, you get 1, 2, 3, 4, 5, 6, 7, 8, and you're done. Okay, that's merge sort. So, any questions about the in-memory merge sort? Like the general idea is not how to actually implement it. Like the general idea, you divide and conquer, right? So to adapt that to an external memory, so basically you can just do like when you are dividing your arrays, suppose you still have a huge file. So let's say you have a
huge file here, and this file has a bunch of pages. Okay, so in each page you might have multiple elements like 1, 2, 3, 4, 5, 6, 7, 8. Then when you are dividing, you are basically dividing the pages instead of the elements. So you might cut the file into half and half. Okay, and you know this is still a recursive algorithm. Suppose you can get a sorted file out of the first half of this file, and you can also get a sorted file out of the second half of this file. Okay, then what you get is actually two files. They are both sorted. So that's basically you have 1, 2, 3, 4. This is the first file, and you have the second file as well. 5, 6, 7, 8. So this is file 1. This is file 2. Okay. So when you do that, you allocate 3 buffer pool frames here. There's an input 1 that's gonna like pulling one of the page from file 1, and you have input 2. Input 2 will hold one page from file 2, and then you have an output buffer. That's another page frame. Okay, so the minimum you need is 3 page frames. So if you have a 4 kilobyte page, then at minimum you will need 12 kilobytes of memory. Okay, but then you can do whatever size of the sorting of whatever size of file. Okay, suppose you have these 2 files. The way you do that is actually, so initially you maintain a pointer. Okay, you maintain a page ID pointer. So initially you have a page ID here, PID 1 and PID 1 and PID 2. Okay. Initially PID 1 is equal to 0. Suppose this is page 0 and 1, 0 and 1. So initially they are both 0. Then you pull in both the pages into the memory. So basically you get 1, 2, you get 1, 2 here and 5, 6 here, right? That's page 0, both page 0. Then you maintain 2 additional pointers. One points to the first element on the first page. Okay, so that let's say that's called L. The other one is a pointer on the other page. Let's say it's R. Okay, so initially they are basically index 0. That's the like slot ID on your page. Okay, then you basically then you do a loop. You repeat this every time you look at L and R. You try to see which one of the keys smaller, right? So suppose now you see 1 is smaller than 5. Then you put this 1 into the output buffer and increment the corresponding pointer. Okay, so that's L. Initially it's 0. Then once you choose 1, L is updated to 2. L is updated to 1. So it's now pointing to 2. The element 2. Okay. Then you do a comparison of this 2 and 5. 2 and 5. These 2 keys. Since 2 is still smaller than 5, so you increment L again and put the 2 into the output buffer. Alright? Okay. So now 2 things happens. The first thing is the output buffer is full, right? Suppose each of your page only holds 2 elements. Then basically now your output buffer is full. And you know this is already sorted, so you can just bump that to the disk and clear everything. So basically you write this output, the buffer page, a buffered output page to the disk, and then you clear the output buffer. Okay. Then the next thing to do is increment L. But notice that once you increment L, if it becomes 2, it's out of range of the page, right? What happens is that you increment PID 1 to 1, okay, and bring in the next page, okay, into the buffer frame 1. So basically, you pull in 3 and 4 here, then we set the pointer L to 0, Okay, and you continue this process until you deplete all the tuples in both files. Okay. So one special case, if you finish L first, but the R hasn't finished, then you need just append everything in the remaining of the file 2 to output. Okay. Then once you've done that, you get a sorted file here. 1, 2, 3, 4, 5, 6, 7, 8. Right. So it's sorted. Okay. That's the general idea. Okay. So to illustrate that, here's an example. So basically, you have multiple passes. Okay. The first pass is basically you reading every page on your original file, then do an in-memory sorting. Okay. So basically, the pass 0, you reading every page of your input file, then do an in-memory sorting, use whatever algorithm like quicksort. Okay. So suppose initially your data is like this on the first line of the input file line, this line. Okay, so the dark square there means that basically it doesn't contain any data. That's not part of the file. Okay, so suppose each page contains 2 elements, and then once you reading like the first page 3 and 4, you do a quick sort on 3 and 4, and you get 3 and 4. And then you're reading 6 and 2, the second page. Then you do a quick sort on that and dump that to disk. So you get 2 6 here. Okay. Once you finish the process, you get a whole bunch of sorted pages. Okay. Inside the page, elements are sorted, but as a whole, it's not sorted. Okay. Then you do this. Since you have a bunch of, we call this sorted pages now as rungs. Okay. They are called rungs. So basically, a rung is a sequence or a sequential set of pages in which the elements are sorted. Okay. So now the rung size is basically 1. Each rung has 1 page, and inside that 1 page, everything is sorted. But across the rungs, it's not sorted. Okay. Then once you have the rungs, you can merge every 2 rungs into a larger rung. Okay. So to do that, so basically you do the previous mentioned the merge process here. Okay. So you merge the first 2 rungs, like reading them into memory and do a linear scan over them. So you get a sorted run 2, 3, 4, 6 over here. Okay, so over here. Then the next thing happens is you deal with the next 2 runs. So basically you're reading 4, 9, 7, 8, and you get once you get it sorted, you get an output of 4, 7, 8, 9. Right? It's the second one, and so on. Okay, so once you finish the pass 1, you get a whole bunch of rung of size, at most size 2. Okay, each rung has 2 pages, and inside each rung, the elements are sorted. Basically, so in the first rung, it's sorted. It's in the order like 2, 3, 4, 7, 4, 6. It's already sorted. But across the rungs, it doesn't necessarily. It's not necessarily sorted. Okay, this is pass 1. So after that, since you have now in this case you have 4 rungs, and each rung has at most 2 pages, and then you further merge every 2 of them into an even larger rung. So that's pass 2. So basically, you do the merge process we mentioned before, like you have 3 buffer frames. You do that, and then you get a larger run out of the first 2. So it's here. Okay. Once you're reading the first 2 rungs and you do a merge process, you get 2, 3, 4, 4, 6, 7, 8, 9. Okay? And you do the same to the next 2 rungs. Once you do that, you get 2 rungs of size of up to 4 pages. Okay? And then you do the same. Basically, you merge these 2 rungs using the very same merge process, and you get the final result. Okay, so that's the basic idea of a 2-way merge sort, right? So the cost of this. So if I'm to compute what's the I/O cost for that, How do I compute that? So for actually observation for that is for every pass, you read every page once and you write every page once. Okay, and the number of pages is exactly the same as your original file. Okay, why is that? Like for pass 0, you basically read every page once and sort them and write them to disk. So that's basically read once and write once. For pass 1, you read every page here, which has the same amount of pages as the previous as your input file. So you read every page once, and then since you are dumping the merged runs onto the disk, it still has the same amount of pages, right? So if you are merging 2 pages, you get 2 pages. If you are merging 2 rounds of 2 pages, that's 4 pages in total. Then you get a round of 4 pages. Okay, so the number of pages in total doesn't change. Okay, so basically for pass 1, you still get to read every page once and write every page once. Okay, so that actually holds for every pass. So that holds for pass 0, pass 1, pass 2, pass 3. And so the cost for a single pass is basically 2 times the number of pages. Okay, because you read everything once and write everything once. The next thing is how many passes do I have, right? The number of passes is actually the height of this tree. If you view this is a binary tree, right? So in general, if you have n pages in the input file, then the height of the tree is basically log 2n. And let's take a ceiling, okay? Actually, I should write n over b, right? In our previous notation, we write n is the number of tuples, and b is the number of tuples you can hold on a page. So the number of pages would be, this is the number of pages in input file. It's n over b, okay? So then your height of tree is basically log 2 n over b and take a ceiling on that, right? That's it. So then what's the total cost? The total cost is basically the product of those two numbers, right? So that's basically 2 times n over b and times log 2 n, right? Plus 1, sorry. Plus 1, right? Because you still have a pass 0. That's something that's likely to be neglected. Because when you compute the height of tree, you are only counting the ladders merging 3 levels. Okay, the three passes for merging, but you didn't count the first pass to do the like in-memory sorting part. Okay, like the intra-page sorting is in the pass 0, so you need to plus additional 1 here to account for pass 0. Okay, so that's about it. So the total cost will be 2 times n over b times log 2 n over b plus 1. Okay, that's the total cost. Correct? So, okay, that seems already solved all the problem we have, right? So if that's the end of, if that solves our problem, then this lecture is over. Okay. But actually, so there's more problems with this approach. Like first, you didn't actually fully utilize your memory, right? We said you need at least 3 buffer pool frames. But what if you have much more? You have like 1 megabytes of memory, but you only utilize like 12 kilobytes. That's a huge waste. But can you utilize more memory so that you can make this process faster? Right? That's something to be solved here. Okay. So actually, we can use all the memory. Suppose our memory has a size of n, and each page has a size of b. Okay, that's in terms of either bytes or number of tuples. Okay, So that's basically M over B is the number of main memory frames we can have for sorting. So instead of doing this in a two-way merge sort, we can do that in a much many more ways of merge sort. Okay, so that's k-way merge sort. Okay, so basically, the first thing we need to solve is that we don't have to only read one page at a time at pass 0. Remember, at pass 0, what we did was we reading every page once and do a quick sort on that page and write it back. But actually, if we have M over B main memory buffers, then what we can do is we read every M over B pages from the file. Then we can basically do a quick sort on that, right? If I have a file of N over B pages, then that will reduce by number of runs from N over B to N over N. Right? Let's see an example. Suppose N over B is 1,000, right? So if I just reading one page at a time and do a quick sort on that page and write it back, then I end up with 1,000 runs, right? Alternatively, I'm reading every M over B pages. Suppose this M over B is 5. Okay, I can hold that at most 5 pages in my memory. Then, how many rounds do I have after this? Basically, I'm reading every 5 pages and do a quick sort on that and write it back to this. So then, I only end up with 200 rounds, right? That's 1,000 divided by 5. Okay. So since you start with fewer rounds, the fewer number of merges you will have later, right? Because it's the number of rounds is actually the this part, right, in your calculation. Okay. So even if I just modify the algorithm like this, it's already better than the previous approach, right? Because you reduce the number of rounds you need. So, sorry, the number of passes. This is the first thing to do. Then for the merge, we were actually not utilizing the whole memory as well, right? So what we could do is that since we have M over B buffer pool pages or buffer frames, so actually we only need to reserve one of them as the output buffer, but allocate all the others to the runs or to the multi-way merge process. Okay? So basically, for each way or each run, we allocate one buffer frame here. So you can take at most M over B minus 1 runs at a time. Okay. So basically, what happens is that this is the first one is a run. Okay. So each smaller square here is a page. So this is page 1, page 2, page 3, page 4 for run 1, okay? And then you have run 2. You still have page 1, page 2, page 3, page 4, and so on, until you get to the run M over B minus 1. Then you have a bunch of pages, right? Yeah. So every time you're taking a page from each of the runs, so basically it's still the same. You maintain M over B minus 1 page pointers. Basically the first pointer points to here, the second pointer points to here, and so on, right? And then you bring in one page, the page that your pointer is pointing to into the memory pool for that particular run. So basically for run 1, you bring in the first page from run 1 and put it here. Okay, so this is the first page. This is page 0 of run 1. And this one will be page 0 of run 2. And so on. So for this one, it will be page 0 of run M over B minus 1. Okay? Then what you do? You basically maintain a whole bunch of pointers, right? Like the slot pointers or the row pointers that points to the tuples on these pages, okay? And then you do a comparison among these tuples you're pointing to. You pick the smallest one. Suppose the smallest one is here. It's on the round 0, round 0. Suppose that's the smallest one. Then you copy that into the output buffer. Then increment this pointer. Okay. So and you repeat this until you deplete all the tuples. Okay. So once if your pointer moves out of range of the page, then what you do? If your pointer moves out of range, okay. Suppose this is the pointer of the first page of the first one, okay, and it's moved out of range. Then what you do is you reset that back to 0 and bring in the next page of row 1 into this particular frame. Okay, so basically you reset that this pointer, the row pointer back to 0. Then you increment the page pointer of round 1 to the next one and bring in that page. Okay, and bring in that. And then you repeat this process until you deplete all the pages in all the rows. Okay, so basically in this process, you are merging m over b minus 1 rows at a time instead of just 2 rows. Okay. So right. So then how many passes do we have? How many passes do we need to sort a code file? Okay. So after pass 0, you have n over m rows, right? So that's the initial number of rows. And every time every m over b minus 1 rows gets merged into 1. Okay, into 1 row. So that basically means the number of passes you will need is log n over m over b minus 1. That's the base. And then get n over m and take a city. Okay, that's the subsequent merge passes you need, right?
Why are we subtracting one again?
Why are we subtracting 1? That's because you reserve 1 frame for the output buffer. Okay, you cannot merge m over b rows at a time, but you have to reserve 1 for the output. So that's the number of merge rows we have. So then the total number of rows would be that number plus 1, right? If you take into consideration you still have the pass 0, then for each pass you still only read every page once and write every page once. Okay, it's still easy to see, like if you are merging m over b minus 1 rows at a time, if each of them has a size of d, then the total number of pages will be m over b minus 1 times d. Okay, so suppose you have m over b minus 1 rows, and each one has b pages. Okay, so when you are reading them, you are reading everything once. So that's going to be m minus 1 times d, right? And then you are also writing everything once, because once you merge them into 1 round, the new round will have this many m over b minus 1 times d pages. Okay, so after each pass, the number of pages still doesn't change. Okay, so that means basically for each pass you pay the cost of 2 times the number of pages in the original file. Okay, so that's the total cost. That's 2 n over b times the number of passes. That number of passes actually includes the pass 0. Okay, that's not just the merge passes. Okay, so basically this part is this guy. Okay, 1 plus that number is the number of passes. Okay, so basically the total number will be 2 times n over b times 1 plus log n over b minus 1 n over n. So that's basically the total I/O cost for this m over b minus 1 way merge sort. Okay. So far so good. Any questions about that?
Sorry, can you go over like once again how you got from the 2D something to the 2 MOV?
Oh, that was just explaining why the number of pages doesn't change. Okay, so basically, if you are merging m over b minus 1 once, you are merging this many rounds, and each has d pages. Okay, so basically you have a bunch of rounds, each with d pages. So how many pages do you have in total?
D times.
Right, d times n over b minus 1. And when you are reading them, you are reading like every page once, right? So that's still n over b minus 1 times d. So basically your number of pages in total doesn't change after each merge process. Okay, that's the key point. So that's why in each level we will have the same amount of pages as the input. Okay, so that's why we times this. Yes, yeah. Okay, m is basically the number of tuples you can fit in a page. N is the total number of tuples in the file. And B is the oh, I'm sorry. Yeah, I said it wrong. So I got it wrong. So B is the number of tuples you can fit in the page. M is the number of tuples you can fit in the memory. And N is the number of tuples you have in your file, input file. Okay, that's the explanation. Okay. Yeah. So let's see an example here. So suppose our m over b is this is m over b. Okay, we have 5 buffer pages, and we have to sort 108 pages. So we get m over b here. Okay. So for pass 0, what's the size of each row? Yeah, it's gonna be 5 pages. That's right. And then how many rows do we have? That's 108 divided by 5 and take 3, right? So that's gonna be 22. So you have 22 rows after pass 0. Of course, the last row of after the pass 0 is only gonna have 3 pages instead of 5, right? Because you only have 108 pages in total, right? Anyway, so for pass 1, how many? After pass 1, what's the size of each row? It's gonna be 5. So you have initially your size of round is 5. Then you merge every 4 of them. So that's going to be 5 times 4. It's going to be 20 pages. It's going to be 20 pages. Then how many rounds do you have? You merge every 4 of them, and there are 22 in total. So the number of rounds would be 22 divided by 4. So that's 6, right? You get 6 rounds. Of course, the last round is not the full size. The last round has 8 pages, right? You get a 20 page round, 20 page round, 20 page round, 20 page round, and 8 page round, right? And then it comes the second pass. What's the size of each round after the second pass?
I have a question.
Yep.
So I was looking on pass 0, why isn't it 4 pages for the size of each run? Because you have one for the output page.
For pass 0? For
Yeah.
pass 1?
So why isn't it 4 instead of 5? Because
This
you have
one?
to have an output.
Right, you are having an output. When you do a merge, you have to have a reserve of output buffer for that. So you can only merge up to 4, in this case, 4 rounds at a time, right? But for pass 0, it's different. It's not merging. You're basically reading every 5 pages and do an in-memory sort. You don't need an output buffer for in-memory sort, right? Then you write it back. So that forms the right?
That makes sense.
That's the okay. So Yes. So for path 0, you basically do the same, continue the calculation, and in the end, you end up with 3 passes, right? Right. Sorry, 3 merge passes, 4 passes in total, but 3 merge passes. Right? You finish everything in pass 3. Okay, so what's the total number of IO paths? So it's going to be 4 times, since you have 4 passes, and in each pass you read every page once and write every page once. Okay, so that's going to be 4 times 2 times 108. It's going to be 864. Right? That's the total number of IO paths. So any questions so far about this? Oh, I explained that here. So basically, this 5 is m divided by b, and this 8 is n divided by b. Okay. So we are already talking this in pages. We said we have 5 buffer pages. We have 108 pages in your file, input file, right? So that's already n over b and n over b. Minus 1? Minus 1? So minus 1 is happens here. So basically, since your m over b is 5, right? What's m over b minus 1? That's 4. So that means basically you are doing 4-way merging. In every pass after pass 0, you merge every 4 rows from the previous pass. Okay, so that's why we have a 4. Yeah, that's where that minus 1 comes in, right? And you do this whole bunch of stuff here, and then you end up with 3 merge passes or 4 passes in total. Okay, you have 4 passes in total, and in each pass you read everything once and write everything once. So that's why this is the total IO. 4 passes times 2 times the number of pages you have. That's 108. Then you get this one. Right? Still confused? Yeah, I think we can move on. Oops. Anyway, let's do this. So let's see how many passes do you need to sort a particular file of different sizes. So suppose this table lists this column. The first column is the size of the file. It's basically how many pages you have in your file. Then we try different size of our memory. Like here, m over b is the number of buffer frames you have in memory. So this is you just have 3 frames. Then you are doing 2-way merging. This is 5. Then you are doing 4-way merging. And this is 8-way, 16-way, and so on, right? So even if we only have 3 memory buffer frames, we end up with a fairly small amount of passes, right? So even if your size of file go up to billion pages, a billion pages is huge, right? A billion pages is like, suppose each of the pages is 8 kilobytes. Suppose each page is, I don't have anything to write. I have to use this. Okay, I'm sorry, I have to go back to the board because I damaged the pen. Anyway, So suppose each of your page has 8 kilobytes, and you have a billion pages. That's going to be huge, right? That's going to be 8 times roughly 10 to the power of 12 bytes, right? And that's about bytes, kilobytes. Let's see. How many bytes do you have in a gigabyte? That's 10 to the 9, right? Yeah, this is going to be 8 terabytes, right? This is going to be 8 terabytes. So you see, in our typical desktop, you only have a 1 terabyte hard disk, right? So this is like 8 times of that size. Even if you have this such a large file, and you only have 3 buffer frames, that amounts to 3 times 8 kilobytes. That means basically you only have a very small memory that only has 24 kilobytes. You can still sort the entire 8 terabyte file in 30 passes. Okay, that's actually acceptable, given you only have a small memory, right? And if you increase your memory size, which is quite normal in today's architecture, like if you have 257 frames, and each one has 8 kilobytes. That's roughly that's roughly 2 megabytes, right? That's roughly 2 megabytes. 2 megabytes of memory is definitely available on today's machine, right? If you have that many memory, then it only takes like 4 passes to sort this 8 terabyte. Okay, it will run really fast, okay, compared to the file size. And another thing to note that is the higher the number of memory buffers you have, then the fewer passes you will have, and it is as well for the I/O cost. Okay.
So realistically, given that you have like enough memory, but then you have multiple cores that share that memory,
Right.
how can you realistically do parallelize some of the merges so that's less than k?
Yes,
But
that's
then-
definitely one way to do that. You can, of course, parallelize several merges and parallelize the pass level, right? But one thing to think about parallelize this is to, by parallelizing it, you are essentially paying a lot of random IOs, right? That's an issue to consider. So you need to be careful about whether the random IO is worth it, right? If your file is really, really huge, and so that parallelizing it will minimize your CPU cost, and random IO is not an issue here because it's the overhead is small compared to the CPU overhead, then it's fine, right? Or you could have some kind of good scheduler, so that, or you have some spare disks, so that you can spare your IOs onto different disks. That's fine, right? So that's that all takes. You should all be taken into consideration when you design external software. Yeah.
I was trying to think of a way to apply this to what you do in a database. So if I were to sort by star on just a huge table, right? That's what a database would implement to answer that query.
Yes and no, actually. So the database will decide whether this file entirely fits in memory. So if your memory is large enough and you do have those 3 memories to sort it in memory, the database will basically sort it in memory. If it's not, then this is the argument. Okay. Alright, so far we only talked about I/O. We might also want to think a little bit about CPU cost. Okay? 2 things that might contribute to a huge CPU cost. The first thing is let's do this first. Okay, the first thing is let's go back a little bit here. So when we are doing merges, on the m over b minus 1 box, we said we need to find the smallest elements among all the current elements pointed by those pointers, right? So how do you actually implement?
Priority.
Sorry?
Priority.
Right. So if you use a priority queue, it's just log m over b minus 1 constant, okay? And it's going to be much cheaper than you just do a linear scan of all the rows. Since like this is important, why? Because suppose you have a huge memory which has like say just a million pages, and you are trying to do a million run, a million way merge, right? So the issue is basically every time you try to find the smallest number, if you just do a linear scan, that's a million access of memory. It's not cheap, right? So if you use a priority queue, then basically you pay a log a million cost. That's a lot of better. That's roughly like 20 access. Okay. So that's the way to optimize that. And so that's one thing about this merge process. How do you use the priority queue to reduce the CPU cost? And the other thing is, can we have a larger run initially? Can we produce a larger run in the first pass? Okay. So let's see an example. This example is actually it's really this might have the second use. It's good I bring some paper towels. So let's say initially you have a sorted file or almost sorted file. Looks like this. So it's going to be 1, 2, 3, 4, 5, 6, 8, 7. Okay, that's just an example. So suppose your file looks like this, and it's almost sorted, right? But still, if you are doing a two-way merge, it's basically going to cost you pass through like 3 passes, right? You're still gonna end up with 3 passes. So the number of files, what's the number of files? It's gonna be 3 times 4 times 2, right? It's gonna be 24 items. Well, can we do better? Can we produce a larger one? If we know, so suppose you know this file is almost sorted. The most naive thing to do is basically you start reading the file and see whether it's sorted, right? If it's already sorted, you put that into the cart log. So in that way, basically you're reading 1, 2, find it's already sorted. Then you're reading 3, 4. 3 is larger than 2, so it's still sorted if it's put into the first one, right? Then you do the next, and once you reach the 7 here, it's out of order, okay? So then you just end up with one run, and that has 7 elements, so that's going to be 1, 2, 3, 4, 5, 6, and 8, right? This is run 1. And you have a second one that only has 1 element, that's 7, okay? If you do that way. And yeah, this is just a heuristic, but this is not good in a general case. Because if your file is truly random, then most likely you will end up with a lot of small ones, right? If you do it this way. So how do we actually mitigate the problem, like achieve the best of both worlds? Okay, and then this is something called the tournament sort. I don't like the other name. It's called heap sort. It kind of like conflicts with the real heap sort, right? Use a priority queue or link heap to do the sort. But this algorithm, I prefer the first name, tournament sort. It's like some kind of tournament because every time you, let me explain this way. So initially, so if you have m over b, yes, okay, this one. If you have an m over b memory buffers, you reserve m over b minus 1 for a heap. Okay, so this is going to be a heap. This is going to be a heap. And then you reserve one page. This is one page for the output buffer. Okay, so this is the output buffer. Alright. So let's see which one. Yes. So initially, you put everything into this heap. Let's call this heap as H1. Okay. So you put m over b minus 1 pages and put everything of that into this heap. So basically, you are going to have a heap like this. So it's going to be, say, 1, 2, 3, 5, 4, 6. Right? That's a heap. Yes, that's a heap. So basically, that's 1, 2, 3, 5, 4, 6. Right? It's already a heap. Okay, suppose this is the heap. Okay. So every time you remove one element from this heap and put that into the output buffer, and then what happens? And this is H1. Once you remove one element from a heap, you move the last one to the first slot, then do a push down operation, right? So that's basically, it's look like this: 6, 2, 3, 5, 4. So you push the 6 to here, to the smaller one. Right? So you swap 2 and 6, 2 and 6. So it's look like the link heap is looking like this. The 6 is still larger than that, so swap 6 and 4. Okay? So that is it's still a link heap. So after your heap maintenance, you end up with something like this. So that the smallest element is still at the first element, right? The smallest one is still the first in the array. Okay. Notice that you have one empty slot here, right? Can I do something about it? The way you do that is basically, since you've already like reading 3 pages, right? You know the next page is here. Okay. So actually I can only keep at most m over b minus 2. Why is that? Because I don't want to do something with the next page. So I will have an input buffer. Input buffer. So in this input buffer, I will fetch the next page into the memory. So that's going to be 8 and 7. And I have a pointer on the first, initially you have a pointer on the first row, right? It's 8. Okay? Then what I do is that I compare whether this 8 is larger than this 1 or not. Okay? If this 8 is larger than 1, then I know if I put this 8 into this 1, it can appear after 1. It cannot appear after before 1. Right? So then, what I can do is that I basically insert this 8 into this heap 1, so that it fills the slot. Okay, then your heap is still full. That's good, right? Then the other thing let's finish this. So if I do that, what I do next is basically I remove the top of heap again. That's 2, and I put it into the output buffer. Once the output buffer is full, I dump that to the disk, right? I dump this 1, 2 to the disk, so it's gonna end up here. Then I clear the output buffer. All right. Then I still do a heap maintenance, something like 8. Then push down the 8 to the smaller one of this this child, and then I think we are done, right? So this is still a heap with one empty slot. Then what happens? You look at the next element in your next page. That's 7, right? 7 is still larger than the last element you popped into the buffer, output buffer, right? So it can still appear after that element. So that means you can just put this 7 into this heap again. Okay? Then once you finish the whole process, you can convince yourself you end up with one single one, right? 1, 2, 3, 4, 5, 6, 7, 8. 没有到， you only end up with one bar and you just do this one pass. This is the good case where you have an almost sorted array. But what if you don't have an almost sorted array? Let's say this 8 is not an 8, it's a, let's say it's a 0, okay? What happens when we initially have that? 1, 2, 3, okay? So suppose we were at the point where we just popped out 1 from the heap top, and then we're reading the next page, and we reset the row pointer to this 0, and then we find the next element in your file is actually 0. 0 is smaller than the one you popped from the heap. So what that means? That means if you allow this 0 to be in the current one, it must be before this one. And that's not easy to do because although this is the first page, right? So you can easily do that in memory, but in reality, so in general, this one could be anywhere in your file, in your ROM. You could already have a bunch of pages that's already written out to the disk, so that you cannot like just insert something into that, right? So the only thing that you can do is put the 0 to the next one, okay? But how do you actually maintain that? Because once you go over 0, if you like, let's say I put 0 to somewhere else, okay? Then once you move to this 7 and you pop out 2, what happens? What happens is, you find this 7 is actually larger than 2, then you need to insert that 7 into this heap 1 again, right? And also, notice one thing, you are basically wasting one slot in your heap, right? There are some free space you didn't use. But what's good about heap? A heap is actually, it is a tree structure, data structure, right? But it can be implemented in a contiguous array, right? In a typical way, we implement that from low address to high address, right? That's like you use the, if this H1 is an array, then this is index 0, 1, 2, 3, 4, 5, right? But also you could also do like start the like maintain the heap from the high address. Okay? So whenever you have some free slot here, you can use those free slots as another heap. That's called H2. Okay? So what's that for? That's for everything that doesn't fit in the current block. Okay? If you find, suppose here, you find 0 is smaller than 1, so that it cannot fit in the current one, you put that into the second heap. So what could happen? It could happen like, so once you remove a bunch of elements from the top of H1, you could end up with some next element that's smaller than the current the current one, right? The current one you popped out into the output buffer, right? Then what you do, since you have by then you should already have an empty slot in H2, right? So just between H1 and H2. Then you basically reassign the empty slot to H2. You don't need to do any reorganization, it's just a logical reassignment, right? Because H1 grows from top to down, from low address to high address, and H2 grows from high address to low address. So that's why you can just reassign that particular empty slot, which is just between H1 and H2, to H2, right? Then you have a heap. Then once you clear out everything in H1, so suppose your H1 runs out of elements, nothing is there. what you get. Either you run out of elements in your file, or you have a full H2 H2 is full. Then you start a new run, you can immediately swap the row of H1 and H2 and do the same. Right? So that's the tolerant sort algorithm. Okay? So that's the pseudocode here. So what's let me put it this way. So what's good about this algorithm?
Just do one pass through the file. And
Yes, but
or
originally we also only had one pass, right? Originally, if I just read every m over b pages, I still only do one pass of the file. But here, we still could end up with multiple runs. But there are two benefits. First, if your file is almost sorted, then I get only one run, right? Then I just do one pass. So that's cheap. Or if your file is not sorted, but on average, I can expect it has a larger run size than I normally do. Okay, so actually it can be proved that the average length of a run after a tolerant sorting algorithm is 2 times m over b minus 2. Okay, well, what's that? So m over b minus 2 is the number of pages you assign to h1 and h2, the two heaps. Right? So you can expect the expected number of pages per run is 2 times that. Right? So typically this m over b is not like 3, it's a slightly larger number, right? It can be like 1,000, right? If it's 1,000, in the original algorithm, basically you end up with a bunch of 1,000 page runs. But here you end up with, on average, a bunch of 998 times 2 page runs. Okay, it's almost 2,000. So you effectively like reduce the number of runs of your first after the pass 0 to half. Okay, so that means actually you pay less idle cost later, right? Why is that? Because remember the original number of passes would be log n over m minus 1 n over m, right? This part is actually n over b divided by m over b, right? Something like that. So now you are essentially multiplying the denominator here by 2, right? So that this number is getting smaller. Okay, so actually it's this, but it's going to be smaller. So since initially you have fewer number of runs, you end up with fewer number of passes, merge passes, right? So that your total cost is going to be smaller. The total cost will be like this, right? Because you increase that, this number is going to be reduced, and the total number of passes is going to be smaller. Okay, so that's the main two benefits of this tolerant sorting. You get larger runs, fewer runs, and if your data is almost sorted, then you just do it with one pass. No, it's not possible because an element can always go to the second. Why is that? Because you are only working on the current one. The next one, you haven't written any elements of the next one, right? So you can insert whatever you want.
So, in like the worst case scenario, if it was completely swapped,
Right.
that
Then-
would just be a normal.
Right. Then it's slightly worse than the original algorithm. Because in worst case, if the entire array is completely reversed, in reverse order, then each run will have the size of m over b minus 2. Right? Every time you see one, you put that into h2, so that you only have m over b minus 2. Okay, that's the worst case. But that's actually a small cost to pay because it has a log factor. This in the log, minus 2 doesn't contribute
max length is the entire file.
Right. The max depth is basically entire file. If it's already sorted, almost sorted. Right. So that's term sort. Okay. Any questions so far about this?
What are the answers to those questions?
Oh, so yeah, don't worry about the snowplow analogy. I don't find it's really convincing to me. But if you want to know that, I would suggest you Google it. And I think there's a Google group somewhere. If you just Google it, it will pop out. They will have a detailed description of this snowplow analogy. The worst case is basically the minimum length, as I said, is m over b minus 2. And this only arises when you have a completely or almost completely reversed file, like your file is sorted in the reverse order. Okay, and the best case will be in the entire file. If your file is completely sorted or it's almost completely sorted, right? Then it's most likely it's going to be you only have one row, and that row has the length of the file. So, okay, about this. So there are some further optimization opportunity for external sorting related to other stuff like. So basically, in our original description, whenever we run out of some like input page, we do a blocking IO, right? We read the next page. That's blocking. But in reality, we actually could do double buffer, right? What's double buffer? Do I have a picture? Right here. So basically, I just like use half of my entire space, my main memory, and then I reserve the other half for IOs. Okay. So when you are working on like the main copy, like input 1, input 2, input k here, these guys there are asynchronous IO issued on these guys. So basically, while you are working on the say the first page of 1.1, you issue an asynchronous IO on the second page to put in input 1 prime. Okay. So once you finish working on the first page of 1.1, you can immediately swap the row of these two. Then you do not need to wait for the IO to complete to work on the next page, right? And then once you do that, you just issue another asynchronous IO for the third page, right? To fetch that third page into the input 1, right? And we could do this as well for the output buffers here, right? So basically, when this output buffer is filled, I have to first dump it to the disk, then clear it. Then you can continue with the merge process. What if we reserve some a double buffer for that? We maintain a second buffer. So whenever this output fills up, I swap the row of the two. Then I issue an asynchronous write to the disk. Then you don't have to pay the blocking write cost, right? So that's gonna be better. And also, this is not necessarily just 2 pages. You could also do this like three standby buffers, right? You could have 3 frames for each of the run and 3 frames for the output as well, right? And this actually can be configured. So basically, that actually how many buffers you need for each of the run or the output actually depends on what hardware you have. So suppose your hardware is reading or writing to your hardware is 10 times slower than the speed of your depleted page. Then probably you need to keep 10 standby pages for that. That's the optimization called double buffering, just for the purpose of overlapping CPU cost and IO cost. Okay. And the last thing, the very obvious one is, why don't we just use the B plus tree for sorting? Because your data entries are sorted, right? The original goal of B plus tree is to have a sorted range, right? But why don't we just use that? Random IO, right? That's the basic issue. So if you have an alternative tube, then it's bad. You have a lot of random errors, and it can be potentially significantly slower than you do merge. So that's it. Okay, that basically summarizes this lecture. So we talked about external sorting, the two-way merge sorting, k-way merge sorting, then how do we actually reduce I/O cost and CPU cost. Okay, that's it. The end of this lecture. See you next time.
That's actually from the sequel.
You can see and previously they had yeah, I know. Okay, so basically, no, it's a database standard. It's basically
We did that last semester and then you read different papers out.
Oh,
So
yeah.
I wanted to take that version, but I think also myself.
Yeah, so it's definitely
so the remember
It's just been multiple. It seems like that's just a long stage.
Yeah.
Yeah.
yeah, really. It is. So actually talk about like
I just really walked through.
yeah, so I didn't really want to do this.
It's also cool, like trying to maintain as like professional stuff.
Yeah.
And like different versions of it.
Right. It's just I don't know if you have time for that.
Oh,
So yeah, maybe I'll just follow something.
you can send a survey on this film.
Yeah.
Like there's also just like incredible
Yeah, right.
It's like almost like I want to watch these video lectures and understand it.
Oh,
I don't think I don't have a good enough accent.
Yeah, I could also like to say a bit of bigger.
No, it's okay. Just do whatever's whatever.
I don't just be
Yeah. What do you expect? It's just like
yeah. Basically, he told me that I'm excited to go right.
okay, so
For yeah, I'm still